birth. We could say that it is the birth of supersymmetry in the Western Europe. No, I mean, because I will show some reference later on. So I mean, just to let you know that supersymmetry was actually born in ex-Soviet Union, no, in 71. But I mean, I have given this title, Truth, Fact, or Fake, because there is a lot of stories about supersymmetry. It has not yet been detected in the form of particles, but there are many results interesting about supersymmetry in other areas that it's not particle physics, as I shall be showing. No, I just would like to clarify that I wrote my slides in Portuguese language because I know that you can follow, but I mean, I will be speaking in English, and I will make very little reference to the text, as you are going to see. So, I mean, this year we have very nice celebrations, physical celebrations. No, it is the centenary of the duality wave particle, no, the doctor thesis by Louis de Broglie. It is the centenary of the birth of Paul Feyerabend, who was a very important philosopher of physics. 70 years of the Young-Mills paper. So it's something that we should celebrate. 60 years of the heavy works on the Higgs mechanism by Higgs himself and others. 60 years, no, of the proposal by Gell-Mann and Zweig of the existence of quarks. 60 years of the discovery of the CP violation in the weak interactions by Cronin and Fitch. 50 years, 74, no, of the works by Polyakov and Toft about non-abelian monopoles. 50 years of the very important discovery of the charm of the charmed quark at SLAC and the Brookhaven National Laboratory. 50 years of the, I would say, of the presentation and consolidation of the standard model of particle physics, and finally, 50 years of the pioneer papers on supersymmetric field theories by Vesumino and Salam and Strasdy. So I think this is something that deserves now some reflection on SUSY, how it could appear in accelerators, where can we find SUSY, what are the true signals for the existence or not of SUSY, you know? Just coming back, you know, supersymmetry was born actually in Soviet Union. These two papers are, we should say that are the fundamental, I would say the DNA papers of the supersymmetry. The paper by Goldfund and Lichtman, and the paper, and this other paper by, I forgot the author, I didn't put the author here, but okay, it's a Russian paper too. So they were trying to introduce new sorts of fermionic variables in the Poincare algebra. And this paper on the Goldstone particle, if the neutrino were a Goldstone particle, because neutrino is mass, in the standard model, neutrino is considered to be massless, and it has spin 1/2. So the question was, I mean, at that time, could the neutrino be a sort of a fermionic Goldstone particle, not a bosonic, not a spin 0, but a spin 1/2? And these, I mean, these sort of questions were the ignition process for the birth of supersymmetry. But in the Western, supersymmetry started directly in field theory. So the two basic works are the works by Vess and Zumino, supergauge transformations in 4 dimensions. So they are able to write a supersymmetric field theory in 4 dimensions, and the supergauge transformations by Salam and Strasdy. So, I mean, these two papers here, we could say that they are the original papers. They are the papers which signal the discovery of supersymmetry in the Western, never forgetting these two important papers from Soviet Union. Now, some other papers, I mean, at that year, 74. So we see that 50 years ago, there was a lot of already motivation to start supersymmetry, to study and to start studying supersymmetry. This paper by Salam and Strasdy, when they studied the representations of the supersymmetry algebra, and the paper by Ferrara, which is a very important paper too, where he connects supersymmetry to the six-dimensional hypercone. Why six-dimensional hypercone? Because the six-dimensional hypercone is connected to the conformal group of 4 dimensions, SO24, as I will show, I'll show later, I will present later on. Also important in 74, this paper by Vez and Zumino, where they write the famous Vez-Zumino model. Now, the Vez-Zumino model is a Lagrangian theory, a Lagrangian model, where we have fermions and the scalars. We have no gauge interaction in this Vez-Zumino model. We have fermions and the bosons interacting a la Yukawa, and we have also the lambda phi 4, the self-coupling of the scalars. So it's the generalization, let us say, it's the most general supersymmetric model with all the renormalizable interactions in 4 dimensions. And this paper by DeWitt and Friedman is also a reference paper in the birth of supersymmetry, phenomenology of Goldstone neutrinos. Okay, and so these are important. I would say that this paper should mark, should outline the discovery of supersymmetry. Now, I mean, we have to ask, in which scales we should be searching for supersymmetry. So we can, I mean, in general, we connect supersymmetry directly to a more fundamental level, to the scale of the fundamental particles. So, but I will show you that there was and there is still a lot of activity in connection with supersymmetry at a less fundamental energy level, let us say at the atomic and at the nuclear scales. Supersymmetry also in connection with the objects which has a topological nature, like monopoles, sphalerons. So there is nowadays, in this third run of the LHC, some activity in the Moedal collaboration, searching for signals of supersymmetry through the electroweak monopoles. Also, supersymmetry appears nowadays realized in a sort of emergent supersymmetry in condensed matter physics. And now we have more recently some sort of laser arrays which show some supersymmetric behavior, or which can, let us say, realize some quantum mechanical supersymmetric behavior. So this I think it's not so important. I think we should I should organize the development of supersymmetry around in terms of phases. So the first phase, I will call it the historical phase, is the pre-Seiberg-Witten. It's the phase and the development of supersymmetry between 71, 74, and 94. The first 20 years of SUSY was going in some direction. After the important paper by Seiberg-Witten, this paper, which is 94, there was the direction of supersymmetry took a different way. But it's still searching for supersymmetry in particle physics. And also, after the discovery of the Higgs in 2012, we started the second run of the LHC, and the parameter space of supersymmetry is getting more and more restricted. And now we have the third run in progress until 2026. It seems that LHC will operate until 2041. So perhaps we have some more 17 years, 17 years of LHC operating in search, for example, of SUSY2, dark matter, monopoles, but maybe searching for supersymmetric particles too. So, I would like, I'd like to show, or to motivate. Oh, I'm sorry, let me put it here. I'd like also to motivate supersymmetry by saying that when it appeared in a sort of scenario, in a sort of framework, I mean, which was very, it was a very hot period of quantum field theory, because quantum field theory was being reconsidered again after the discovery of the asymptotic freedom at the deep inelastic scattering at Slack. No, because there was a sort of exile of field theory in the 60s. No, I mean, because there was the dominance of the S-matrix theory, bootstrap formalism. So supersymmetry appears in the beginning of the 70s, together with many important points, many important topics, and many important sub-areas of particle physics. For example, there was an intense activity in conformal symmetry. Why? Because due to the experiments at Slack, deep inelastic scattering revealing was unveiling the dilation behavior, the conformal symmetry, was a good symmetry for high energy physics. So this opened up a very important period of research in conformal symmetry. Formulation of QCD. So QCD comes together with supersymmetry, though they are disconnected topics, no, but they appear together in the same period. The November Revolution, 74, with the discovery of the charm, the normalization of Yang-Mills theories, and the consolidation, the formulation, the final formulation of the standard model describing QCD and electroweak interactions. So supersymmetry appears in this scenario. It was a very historical scenario because there was a revival of quantum field theory after the discovery of the scaling behavior in the deep inelastic scattering at this Slack. So, okay. But let me tell that perhaps it's important to see supersymmetry. Also, I would say, fora da caixinha. In Portuguese, this means out of the little box. So we are talking about supersymmetry, not in our context of field theory and particle physics, but to show that supersymmetry, is beyond the limits of particle physics and quantum field theory. So when we talk about atomic and nuclear physics, we have this very classical paper by Franco Iachello. I think he was working at Yale. He's from Napoli, but he was a professor at Yale. Where he studied the application, of supersymmetry. He discovers, let us say, he understands that there is a supersymmetry behavior, a supersymmetry underneath the behavior of some categories of nuclei. So it was the first application of supersymmetry to nuclear physics. There is also this paper by Iachello, dynamical supersymmetry in nuclei and supersymmetry in nuclear physics. I think it's a very instructive paper for students. Sometimes we want to understand how supersymmetry appears in other areas. So I think this paper by Iachello is very good because it's very pedagogical. It really teaches, we can really follow Iachello when he tries to explain why he claims that there is a supersymmetry in nuclear physics. Also, Nambu types of BCS theories, the works by Nambu on the fermion boson relations in BCS, the superconducting type theories. This work published in Physica in 1985, and this proceeding supersymmetry and superconductivity. So already some trials, some attempts to apply supersymmetry in connection with problems in condensed matter physics. So it's not supersymmetry in particle physics, but supersymmetry in condensed matter physics. It's still out of the box. I can quote this very interesting physical review, very instructive physical review by Cooper, Kerr, and Surratam, Supersymmetry and Quantum Mechanics. So they show how to solve some problems in quantum mechanics by applying supersymmetrical methods. So, it does not, we are not claiming here that supersymmetry has been discovered in quantum mechanics, but supersymmetry can offer some, let us say, some mathematical tools to solve complicated and nonlinear problems in quantum mechanics. There is also this paper this book, this book by Juncker, Supersymmetric Methods in Quantum and Statistical Physics. So how to use supersymmetry, the concepts of supersymmetry, or to solve problems, to describe problems in statistical physics and basic statistical physics and quantum mechanics. Also, still out of our box, our particle physics box, we have this paper, 2010, simulating the Vesuvian supersymmetric model in optical lattices. So application, a sort of realization of this field theoretic model introduced by Vesuvian back in 1974, applied to optics. Another interesting paper, this paper by Kevrekidis, nonlinear application of supersymmetry in nonlinear systems. No, it's a physical review article. Its archive is also available. It's also very interesting. It's a very good work to apply in a course on quantum mechanics, for example. So, I try to motivate, to show that before going to our domain, to show that supersymmetry is, coming over other fields of physics. No? So here we talked about nuclear physics, atomic physics, statistical mechanics. Okay, quantum mechanics too. Now we are coming to our field, supersymmetry in the box of particle physics, 5 pieces, física de partículas, so particle physics and fundamental interactions. So this is, where supersymmetry was first born. In general, we connect supersymmetry directly to particle physics and fundamental interactions. But okay, this is not all. No, so supersymmetry became very important in connections with the standard model and with the particle physics because it gives some very important insight about the stability of the electroweak vacuum. And also supersymmetry offers a good candidate to cold dark matter, which could be one of the neutralini. So there are motivations, there are good motivations to believe or to have, let us say, the faith that supersymmetry could be an important symmetry in our understanding of particle physics and some physics beyond the standard model. We say that the most popular model in connection with particle physics and which is being tested at LHC is this called I'm sorry. Okay, I'm sorry that I'm not managing well to pass here the slides. I think there is some problem. Okay, let me come here. I'm sorry. So the model, which is very important, is this MSSM in various versions, in diverse versions. The minimal supergravity model, all these minimal supersymmetric standard model, this MSSM, which is the model which tries to describe supersymmetry at the accelerator scale, at the TeV, the TeV scale. So it is presented under different versions. For example, this minimal supergravity, this gauge-mediated supersymmetry breaking, anomaly-mediated symmetry breaking, and this P, which is the phenomenological minimal supersymmetric standard model. All these models try to make a connection between the breaking of supersymmetry at high energy and how this breaking is communicated to the low energy sector. These models are different in the number of parameters. The minimal Sugra model has 4 parameters. This phenomenological MSSM, the PMSSM, has 19 parameters. So, if we leave the minimal supersymmetric standard model without any constraint, it may have even 100 parameters. But when we start constraining by putting different restrictions on it, we get these different models, and these are the models which give the scale, the particles, the interactions that are being searched for at LHC. Here, I would like to make a comment. So if, up to now in the run 3, there is no evident signal of supersymmetry. So we could say that the parameter space is being less and less, more and more restricted, less and less broad. So we are losing supersymmetry at the LHC. This does not mean that we have lost, but every time we see the parameter space being more restricted. But what is really being tested at the LHC is not supersymmetry in its full. It's a mechanism to realize supersymmetry and to break supersymmetry. So this MSSM and this zoo of particles it has, all the phenomenological results derived from the MSSM, they are a consequence of a very particular way of breaking supersymmetry. Because we know when we have a symmetry, either it is exact or the symmetry is broken by some mechanism. It can be an explicit breaking, it can be a spontaneous break, it can be a dynamical breaking, it can be a breaking by anomaly. So, I mean, the problem is not to have the symmetry, but the problem is how to implement the symmetry if it is not exact. If it's not an exact symmetry like the electric charge is, we have many choices. We have different possibilities to break SUSY or to break supersymmetries in general. So this MSSM, let us say, it shows to us, okay, it is based on a very particular way of breaking supersymmetry. So if we do not discover all the predictions of the MSSM at the LHC, this means that we are failing to break supersymmetry in this way. But this does not mean that supersymmetry is completely lost. Supersymmetry is much deeper than the MSSM, as I'll try to motivate. I would like to point out here this very interesting paper published in JHAP. I think it's a good paper because it gives also a motivation to keep the faith, or to keep in mind that supersymmetry might really be connected to particle physics. Because in this paper here, the author shows that if we consider the MSSM, we can have a sort of fitting of parameters so that we can stabilize the electroweak vacuum in the 246 GeV scale, as it should be. So, I mean, this paper considers results that we have already got long ago, like the Higgs mass, which was measured at the LHC, the top mass, which was measured at Fermilab in 1995. And so with these results, we can calculate the effective potential of the standard model by using the renormalization group equations, and this would point to a sort of instability of the electroweak vacuum, which would be very bad. But if we call into question the MSSM, we can have a fitting of parameters such that we can stabilize the electroweak vacuum at the 250 GeV scale. So this is an important, result that I would like to call your attention to. So, if someone is interested in some of the references I am quoting here, I can send my slides to Antonio, and Antonio can share with someone, with people who could eventually be interested in considering or reading or knowing some of these references that I'm quoting here. Now, okay, as I already told, supersymmetry started, I'm really quoting again let us say, these papers which signal the discovery of supersymmetry. Vesumino, the Russian papers, the Salam-Strasdy paper. There is an important paper here that I had not yet quoted, but is very important in connection with the origin of supersymmetry, is that Hagel, Opushansky, and Zonius, they discussed in this nuclear physics paper, the most general algebra of generators, no, which is compatible with the S matrix in 4 dimensions, in 4 space-time dimensions. And they get, with that, they get the representation of the supersymmetry algebra. Okay, supersymmetry, which was already studied in the as a supergauge symmetry by Salam and Strauss-D, and a supergauge symmetry also discussed by Vess and Zumino. So they let us say, they generalize the Poincare algebra. So they go one step beyond the Poincare algebra. Poincare algebra contains only the generators of the translations and the Lorentz rotations. No, so we have the translations and the rotations in 4 space-time dimensions. So they introduce they introduced the fermionic generators, and these new fermionic generators, they extend the Poincare algebra to what we call a super Poincare algebra, and they get the particle and field representation of this super algebra. So this is a very important paper which shows us how the supersymmetric particles could be arranged in multiplets. Now, going further, we are talking about 75, 76, we are 50 years back in time. So Young-Mill theories were already popular because, okay, since the paper is 54, but the renormalization of Young-Mills was shown only in 73, 74, no, by as I will show here, by Toft, Veltman, Jambiage, Bolini. So, Young-Mills, people always soon started being interested in seeing how Young-Mills could be formulated in a supersymmetric scenario. And so this opened up very interesting questions, so especially related to these nonlinear sigma models, because we know that the nonlinear sigma models are very important for phenomenology in condensed matter physics, in particle physics, in hadron physics. And so sigma models, they are a sort of counterpart of Young-Mills theories. So, in the sigma models, we can find some Young-Mills symmetry in, let us say, underneath. And so there was a lot of interest in seeing how supersymmetry and nonlinear sigma models could combine, and by consequence, to see Young-Mills too. And this was a very good question for the mathematicians, because by putting supersymmetry in connection with nonlinear sigma models, there appeared a new category of complex geometry that mathematicians had not yet classified, sort of hyperkähler spaces. Okay, mathematicians already know what a hyperkähler complex manifold was, but there was a supersymmetry allowed the discovery of new categories of hyperkähler manifold, new types of hyperkähler manifolds. So supersymmetry started also giving a lot of interest to mathematicians. No? So we are coming to the 80s, and supersymmetry presents one of its most awesome results, which is the first time, they were, some sort of realization of Dirac's dream. What is the Dirac dream? Professor Dirac was always arguing that a finite field theory should be discovered to describe all processes in nature. So Professor Dirac was very stick to the point that a good and complete field theory should be ultraviolet finite, which most of the field theories we know they are not. Standard mode is renormalizable, but not finite. So for the first time, by considering super Young-Mills theory, so putting supersymmetry in connection with Young-Mills and with nonlinear sigma models too, the first ultraviolet finite field theories were formulated in 4 dimensions. So for example, the famous n equals 4 super Young-Mills model, the n equals 2, n equals 4, n equals 2, this a model which has 4 independent supersymmetries. So we have Young-Mills, we have the Young-Mills gauge group, let us say SU3 color, for example, in QCD, but we have additionally 4 independent supersymmetry, or this means that we have 4 independent fermionic generators of this supersymmetry. So in the n equals 2 case, we have 2 independent supersymmetries. This is what we call extended supersymmetries. In 4 dimensions, we can have up to 8 supersymmetries. So n equals 2, n equals 4, n equals 5, 6, 7, n equals 8 is the most extended supersymmetry we can have in 4 dimensions. And n equals 8 can already describe gravity because it includes particle of spin 2. N equals 4 Young-Mills include particles of at most spin 1, so Young-Mills fields. And super Young-Mills n equals 2 also contain Young-Mills fields, but not gravity. Gravity is contemplated only when we have n equals 8 independent supersymmetries. But what I show is that these many super Young-Mills modes like n equals 2, n equals 4 with different gauge groups independently from the gauge group had a trivial beta function, a 0 beta function. This means that no renormalization was necessary. So these are really finite field theories. Now, what a finite field theory could give us in terms of phenomenology is discussable. It's something that is not so clear, but at least we understand how supersymmetry may tame the ultraviolet divergence. So this, because supersymmetry is a space-time symmetry, as I'm going to clarify a little later. So this was a very important period because there was a very intensive activity in terms of finiteness of super Young-Mills theories and finiteness of supersymmetric nonlinear sigma models in 2 dimensions. These nonlinear sigma models in 2 space-time dimensions are renormalizable. So they are not renormalizable in 4 dimensions. They are very good as effective field theories, but not as fundamental theories. But in 2 dimensions, they are renormalizable, and they are the sort of counterpart of Young-Mills in 2 dimensions. So in 2 dimensions, nonlinear sigma models, they are renormalizable, they are asymptotically free, they have topological solutions, exactly like Young-Mills does in 4 dimensions. So these are very important. This is a very important connection between supersymmetry and nonlinear sigma models due to the connection with geometrical properties of complex manifolds, and also with the problem of renormalizability and finiteness. So nonlinear sigma models in 2 space-time dimensions are also finite if we have some sort of extended supersymmetry, n equals 4, n equals 2. So supersymmetry was getting a lot of room in the community due to this properties of finiteness. Now, okay, supersymmetry comes also, now it was important to understand which could be the mechanisms to break supersymmetry. After all, in the end of the day, supersymmetry is not present in our low energy world. So we don't see supersymmetry, signals of supersymmetry in particle physics. So important to understand how supersymmetry could be broken. Edward Witten started the discussing of the dynamical breaking of SUSY in 1981. Also, also these important papers by Dimopoulos and Georgi, and also this line of papers by Dimopoulos, Rabai, and Wilczek, supersymmetry and the scale of unification and the decay of the proton in supersymmetric models. So supersymmetry somehow gives a stabilization. Let us say, it keeps the proton more stable than it is when considered in connection with grand unified theories. So the problem of the proton decay in grand unified theories is, let us say, it's cured, is by the introduction of supersymmetry, because supersymmetry gives a higher time for the proton to decay. So it was the beginning of understanding how supersymmetry could be connected to unification, and also how mechanisms should be understood to break supersymmetry and to try to connect supersymmetry with the low energy scale, which are our present scales. No? Again, so this period, no, I mean, people were studying not only, I mean, they were also very much interested in two other aspects. One, quantum gravity. So there was a lot of activity in quantum gravity at the beginning of the 70s. After this, the standard model was settled down, and okay, one knows that the standard model is not worried about quantum gravity, so it does not contemplate the introduction of gravity. So people understood that Young-Mills is a very good approach, to describe particle physics. So quantum gravity, okay, we knew already at the beginning of the 70s that the Young-Mills also can be used to describe quantum gravity, as the paper by Keeble, for example, paper with Tiama, 56, and the paper by Keeble in 61. So since Young-Mills with supersymmetry combined very well, the idea should be how to see supergravity now, which is one step forward with respect to supersymmetry. So because it is local supersymmetry. Supersymmetry is no longer global, but supersymmetry becomes local, and we get, from supersymmetry, we get the supergravity. And so to understand how supergravity could be connected also to particle physics. So there was a very intensive activity related to simple supergravity. This means quantum gravity with just one supersymmetry. Extended supergravity, so we have more supersymmetries in connection with gravity. As I told, for example, n equals 8. And at that time, people were very concerned also about the Kaluza-Klein theory. There was a revival of Kaluza-Klein theory to understand how these extended supersymmetries in 4 space-time dimensions, for example, n equals 2, n equals 4, could be obtained from a single supersymmetry written in higher dimension. So Kaluza-Klein was rediscovered with the advent of supergravity in the 76, 77. And so this was a very strong activity until 84. 84 is the first string revolution. But I mean, up to 84, Kaluza-Klein supergravity was a very important topic because people, I mean, the community was studying, let me put here, was studying, okay, supergravity in connection with the strings, no? So let me put here again. Okay, here we have already talked about, okay, I'm coming here, okay, here we were, okay, here. So in 84, there was the, I mean, what we call, no, there was the breaking of the, I mean, broke out the first string revolution. No? And so the paper by Green and Schwartz about the anomaly cancellations in supersymmetric D equals 10 gauge theory. Why D equals 10 gauge theory was so important? Because from supersymmetry, a gauge model, a Young-Mills model in 10 dimensions, it gives rise to the 4-dimensional n equals 4 super Young-Mills model, which is ultraviolet finite. So there was a very good connection between one supersymmetry in 10 dimensions and 4 supersymmetries in 4 dimensions. And so this idea of supersymmetry in higher dimension was very fruitful because Green and Schwartz showed that there was a cancellation of anomaly in these models, and so string theories could be free from anomalies, and this was very promising to understand the theory of gravity, okay, in 10 dimensions, okay? So these were the important years, 84, 86, 87. So I mean, people were very concentrated on this on the different formulations of supergravities in 10 and 11 dimensions. 11 dimensions, no, is the let us say the highest dimension to get gravity. I mean, by using supersymmetry. But okay, the highest dimension supergravity theory, 10 equals 11. I mean, also people were studying the, I mean, heterotic string was already formulated, and so there was a connection between this type 1 supergravity in 10 dimensions and the heterotic string, and the supergravities 2a and 2b also in connection with the superstrings. So there was, okay, a very good coupling between supersymmetry in higher dimensions and the string theory. So these were very important topics in the 80s until 86, 87, 87, okay, until 87, 88. Beginning of the 90s, CERN start operating the LEP, Large Electron Positron, which operated between 89 and 2000. Afterwards, it was, I mean, it was disconnected, and LHC started in 2009, you know. So the CERN, I mean, now with this lab, the idea was to make precision tests of electroquick theory and eventually discover the Higgs, which was not the case. Higgs was discovered only at LHC. And so supersymmetry became also, I mean, the supersymmetry community became very interested in the precision tests of the lab, because this could signal some sort of anomalies in the anomalies in, not anomaly, let us say, the breaking of some effects which are predicted by the standard model. And so it could be the signal, for example, for some physics which is not contemplated in the standard model. And this physics could be perhaps supersymmetry. So there was a lot of interest in the lab from the side of the supersymmetry community. Now, important also to say that in 94, there was a sort of a turning point in supersymmetry. Witten and Zyberg and Witten wrote two very important papers in 94, showing that this N=2 supersymmetric Yang-Mills theory in 4 dimensions with 2 independent supersymmetries display a property of the electric magnetic duality. So there could appear in these models a sort of monopole condensation, and this monopole condensation could be connected to the confinement of quarks and gluons. So that was a breaking point in the development of supersymmetry. Supersymmetry changed after these papers by Zyberg and Witten. All these 3 papers which are shown here, and okay, because they soon put the paper in the idea in connection with QCD to try to understand confinement. Also, I mean, this paper by Álvares-Gomes and Hassan is very interesting, because somehow they translate the papers by Zyberg and Witten, which were, I mean, they are very difficult. I mean, they are readable, but they are difficult. So sort of a pedagogical review prepared by Álvares-Gomes and Hassan to give us a sort of guide to understand Zyberg and Witten, and to see how the Zyberg-Witten formulation of supersymmetry with duality could be connected to the problem of the confinement. Now I come back to another very important ingredient, and why I am putting this, it seems to be decoupled from the rest of the talk. I mean, okay, I'm approaching to the end, okay? I mean, the idea that supersymmetry is very close to the problem or to the discussion of the conformal symmetry. Why conformal symmetry is so important? Because we understand that if we go to higher and higher and higher, very high energies, the masses become negligible. And so we approach a situation of dilatation symmetry. We can have dilatation as a good symmetry. So conformal symmetry becomes good at very high energies. So there was at the end of the 60s, beginning of the 70s, a lot of interest in conformal symmetry, because the deep inelastic scattering experiment at SLAC showed this scale behavior, the Bjorken, what we refer to as this Bjorken scaling of the cross sections, showing that there was some sort of mechanism that should be understood that QCD later on described, and it is the asymptotic freedom. So there was a lot of interest in conformal symmetries, and we see how supersymmetry appears in this context. So, in this, I think it's a very good, a very good point to see why supersymmetry, even if supersymmetry is not discovered, detected at LHC, as the MSSM model tries to convey us, it is important to see that supersymmetry is something much more deep. It's something much deeper in connection with the space-time. So people were discussing conformal symmetry because it is a very important symmetry for field theories at very high energies. So if someone wants to get some student, for example, wants to understand or to have instructions about conformal symmetry, I recommend this paper, this little book, by Ferrara, Gatto, and Grillo, Conformal Algebra in Space-Time and Operator Product Expansion. It's a Springer Tracts in Modern Physics. It's a very good work. It's very pedagogical to understand what conformal symmetry is in field theory or in particle physics. Also, this good reference, there is a very good reference by Professor Ivan Todorov from Sofia. It's very, very good reference to also understand the connection or the applications of conformal invariance or conformal symmetry in quantum field theory. Okay. And okay, some historical reference, conformal symmetry was thought much before the deep inelastic scattering in 1909 and 1910. Now, people were already discussing conformal symmetry in connections with optics. Okay, now, what is important here? Why I put this slide here? Supersymmetry is sort of square root. Here, this 1/2 here is an exponent. It's square root of the SO24, which is locally isomorphic to SU22. What is SO24? SO24 is the conformal group in 4 dimensions. It's a 15-parameter group. Okay, it describes here translations, Lorentz rotations in space-time, dilatations, and so what we call conformal boosts. So these are the complete. So here we have 4 parameters, 6 parameters, 1 parameter, and 4 parameters. So we have 15-parameter group SO24. And what is shown? What we show is that if we consider a spinor generator, if we consider some spinorial field, some spinorial parameter, which has this sort here, and this is not something which is coming, just by decree. It's something which is solution to some sort of Killing spinor equation. So if I solve the Killing spinor equation in 4 dimensions, I get some solution spinors, which have this form here. They are linear in the space-time coordinate. And by combining these spinors in a bilinear, as we have here, psi bar, gamma mu, psi, the classical psi bar, gamma mu, psi, the classical for vector bilinear construct in terms of spinors in 4 dimensions. So this generator, with this generator, this 4 vector here, it's a sort of killing vector of the conformal group. I can show that by combining these spinors here, I can generate all transformations of the conformal group. So somehow supersymmetry appears as the symmetry which is underneath, which is behind the conformal group. So this is why we try to understand supersymmetry in connection with this, in connection with the structure of causality of space-time, because the conformal group is the most general group which keeps the structure of light cones in space-time. So if we have a light cone, conformal symmetry, we take light cones into light cones. So it does not it does not break the light cone transformations. So supersymmetry is at the origin of the conformal symmetry. So this is why supersymmetry is very important in connection with the causal structure of space-time. And this is why supersymmetry is very important in taming, in reducing the degree of ultraviolet divergences in field theory, because it touches very deeply the causal structure of space-time. I mean, these papers here by Callan and by Zimanski are very important because they show how we should understand field theory at very small distance behavior, at very small distance regime. So this is conformal symmetry. Conformal symmetry then appears in connection with supersymmetry. And this is very, I mean, for me, this is the most important result about supersymmetry, because one thing is the symmetry. Another problem is the realization of that symmetry. So if we say that supersymmetry is at the roots of the conformal symmetry, this means that independently from the way we try to break supersymmetry, it is already present in this causal structure of space-time. So now, the important is to give some meaning to this symmetry, to connect this symmetry, which is surely a symmetry of the very high energy world, because, I mean, it's conformal. So it is involving dilatation symmetry, conformal symmetry. So supersymmetry is there at a very high energy, but how to connect it to the low energy world? And so this depends on the breaking mechanism that we have to generate, or that we have to invent or to propose. And so this is the problem of the MSSM. If we don't find the particles predicted by the MSSM at LHC, supersymmetry is still kept there in space-time. It is in the causal structure of the space-time. Let me skip some slides here, because I mean, I would like to be back to, I mean, because these are, I mean, developments which were contemporary to supersymmetry and somehow connected to supersymmetry. Renormalization of Young-Mills, renormalization, degeneration of mass. Okay, this problem, I mean, these two papers here were very important tools because, because they were discussing, Giambiagi and Bolini in Argentina and Toft-Veltman in Holland, they were just showing how to renormalize and how to regularize and renormalize Young-Mills theories. And that was a very important point afterwards for supersymmetry, because supersymmetry maybe avoids, try to prevent this field theory from being ultraviolet infinite. Okay, ultraviolet divergent. Okay, so Salam here in 1972, I mean, there was the celebration of the Dirac 70th anniversary. So Professor Salam tried to give this gift to Professor Dirac, presenting how he would conceive a finite field theory, which would appear only 12 years later, in 1982. So Professor Dirac was always quoting that eventually a finite field theory would be discovered for all processes. And so Dirac was also searching, I mean, he spent most of his life searching for, to discuss the origin of the ultraviolet divergence in the electron sector, and to see how we could build up a finite field theory. And supersymmetry, okay, gave this gift to Dirac. Here we have these papers of the presentation of the QCD, let us say the first paper which were presenting QCD, this paper by Fritsch and Gelman, and the other paper by Fritsch, Gelman, and Lloyd Wheeler. I mean, so 72, 73, the QCD Lagrangian was proposed by these authors. Afterwards, the asymptotic freedom. No, and important this because this is in connection with conformal symmetry too. Okay, these beta functions are nothing but the anomaly of its conformal anomaly. You know, paper by Kobayashi and Maskawa showing that a renormalizable theory of weak interaction should contain a third family of quarks, not only two families. So this was very close. 73, supersymmetry was coming from the oven and the discovery of the neutral currents. Discovery of the charm in 1974. And so standard model. The standard model appears together with supersymmetry. So both are nowadays, they are in their 50s. So we have, and these developments were contemporary because they were connected to the same. I think there was let us say, the link between all these developments was the development of Young-Mills theories. So Young-Mills was very important to bring supersymmetry into the scene. And conformal symmetry too. And so supersymmetry appears as a result of a very hot context at the beginning of the 70s. So here I'm not focusing. Supersymmetry tries to solve the problem, the hierarchy problem in the standard model, which is the connect to the naturalness, the problem of the naturalness, and the problem of the gauge hierarchy. So supersymmetry tries to solve some of the problems of the standard model. I'm not going to spend some time on it because I believe that most of the people, students, postdocs know that. So nowadays we can say that standard model is no longer a fundamental theory. Standard model has to be understood as an effective theory. And then the question is, which is the more fundamental theory, which is behind, which is the backstage of the standard model. Supersymmetry is a viable way. Yes, it's a possible way, but there are many other ways. There are higher dimensions, brain world, strings, loop quantum gravity. So there are many possibilities to go beyond the standard model, which is not only supersymmetry. Now, supersymmetry, I think this paper here is very interesting to be read. If someone is interested in understand how supersymmetry could also be detected in the LHC. So this so-called collaboration, this Moedal monopole and exact dark matter at LHC. This paper by Acharya is very important to show how magnetic monopoles discovered in the LHC could signal to a supersymmetry, could give some signature of supersymmetry. Okay, so let me skip here and going to the end. So to show another presentation of supersymmetry out of our box. These are very interesting works, recent works, 10-year-old works, 8-year-old works. The emergence of supersymmetry in three-dimensional Weyl semimetals and two-dimensional Dirac semimetals. So how supersymmetry naturally appears not as a fundamental symmetry, but as an emergent symmetry in condensed matter. The same way it happens to Lorentz symmetry. We see that graphene and many other materials, topological insulators, they display some linear dispersion relations which let us say, which gives some sort of emergence Lorentz symmetry in condensed matter. The same happens to supersymmetry. We have, for example, signals of Majorana fermions that appear in the edges of topological insulators. So, supersymmetry is also now appearing is becoming very popular in the condensed matter community. Also, in connection with laser physics. There are some works, this work was published by CERN Courier in 2019. The title of the paper, First Light for Supersymmetry, because it's a supersymmetric array of, I don't remember, perhaps 17 or 20 lasers, which reproduce the behavior of a supersymmetric quantum mechanical system. This is described in this paper here by Roch Manabadi, a science published in 2019. Very interesting paper because it now takes us to the, let us say, to the photonic. So we can connect supersymmetry now to the photonic. Now this is my last slide. So I'm thank you so much to you people for having being together, no, this 1 hour time. And I mean, my idea here was to show that, I mean, there is, I know that because students sometimes, or even other colleagues come to me and say, oh, supersymmetry has not yet been discovered. So if the LHC does not unveil supersymmetry, this is the end of supersymmetry. So I say, no, what is going on at LHC is a sort of engineering of supersymmetry breaking. We are connected to a very particular way, or to very particular ways of bringing the scale of SUSY breaking at high energies and communicate it to the low energy world, like through supergravity, through anomaly, through gauge interactions. So, I mean, we have some phenomenological model which tries to give us the possibility that supersymmetry be discovered or be present at the present energy scales of the accelerators. But if supersymmetry is not discovered there, we see that supersymmetry may be present in many other branches of physics, like nuclear physics, condensed matter physics, laser physics, no, and statistical physics, quantum mechanics. So, I mean, I would say that, I mean, my idea here was to show that how supersymmetry is spread, no, in the, opening interfaces with other areas of physics, especially now condensed matter, because it's a sort of laboratory laboratory supersymmetry. You can take supersymmetry to a lab and you can make experiments with topological insulators, with graphene, with other semi-metals, no, Dirac and Weyl and the semi-metals, and experience to see how some supersymmetry could emerge. If supersymmetry emerges in these condensed matter systems, it's already a good point to understand this sort of symmetry, which maybe is not easy to detect in particle physics, but maybe it is interesting to understand how it helps us to understand the behavior of these new materials. So, Antonio, thank you so much for the patience. And here I am, okay? I'm open here to have discussions if there are questions or comments. No, not necessarily questions, but I am also open to listen interesting comments that may teach me something or may induce me some sort of new reflection about supersymmetry. Thank you so much to everybody, and let us, I go back to our chairman, Professor Karkaman.
Thank you very much, Jose, for the very nice and very comprehensive review of supersymmetry. Question from the audience? Any question from the audience?
If there is any...
Jeremy, come ahead, please. Jeremy.
Okay.
Jeremy, you're muted. Go and speak, please. Jeremy has some question, and Jonathan.
Okay.
No. I was clapping. It's not a question.
Okay.
Okay. Jose, I had a question. What will be the, for example, in the part in the aspect concerning to condensed matter physics, how will be, for example, the smoking gun signature in the part of the grapheno to see the manifestation supersymmetry in the grapheno? Can you please comment a bit more about that?
Yes, I know. I mean, yes, I know some papers. No, I know some works. No, in which, I mean, in graphene, no, there is it's not a problem, but a sort of aspect of the graphene is that graphene is supposed to be, okay, a planar material, okay, two space dimensions, no? And these, let us say, these graphene sheets, they are not exactly so plain. They have some sort of, they are a little undulations, so there are some waves, no? And I heard, I mean, I read papers in which this sort of this not planarity of the graphene could be associated to a sort of scalar field which people call Kekulé scalar. Kekulé is the name of a chemist. So this Kekulé scalar, how it appears in the graphene, it may, I mean, it seems that supersymmetry, supersymmetry offers a nature way, for example, to bring about this scalar which connected to this, to the electrons, to this, what people call the honeycombs, the electrons in the two lattices of the graphene. And this scalar, which is in there because it could describe that the graphene is not exactly so plain, this comes from supersymmetry. You can, I mean, it does not necessarily come from supersymmetry, but the best way to see the possible origin for this scalar, which helps in the description of the graphene, is supersymmetry, for example. Also, the presence of Majorana excitations could be a signal of supersymmetry too, present in graphene and the other topological materials, these more modern topological materials.
And I had another question: how one can, how is obtaining data? For example, in string theory, one needs 12 extra dimensions to formulate the superstring theory.
I mean, could you repeat the beginning of the question, please?
How one can, what is the reason why 12 dimensions are needed in superstring theory?
Okay. The problem of, I mean, to have higher dimensions in string theory is the problem of what we call the anomaly. So the algebra of generators, I mean, if it describes strings, by fields. So I mean, these fields, they are used to constitute, they are used to build up the generators of the symmetry. So there is an algebra, Poincaré algebra, which is important, Poincaré, because it's connected to relativity. So to close the Poincaré algebra, there is a coefficient in a sort of anomaly term. And this anomaly term, we can make it vanish, and so we can restore the Poincaré symmetry if we fix some higher dimension. For bosonic strings, purely bosonic strings, the dimension is 26. But when we come to supersymmetry, when we come to superstrings, by introducing not only bosonic fields, but let I say, the supersymmetric companions or the supersymmetric partners of the bosonic fields of some string theory, so we have a superstring, the critical dimension, what we call it, comes to 10. So it's only in 10 dimensions that we can realize string theories by obeying the Poincaré algebra, by obeying the Poincaré symmetry, which is very important for relativity. So, I mean, the fact that string theories, let us say, extended objects, they require that they should be embedded in some higher dimension space is in connection with the elimination of the anomaly in the algebra of the generators of the Lorentz symmetry, of the Poincaré symmetry in higher dimensions. So we are always taking higher dimensions in order to be sure that we have the symmetry, the Poincaré symmetry can be realized, and so that this anomaly is absent. It's not, I mean, we don't put higher dimensions by decree. We introduce higher dimensions. We leave the dimensional arbitrary. At the end, when we come to manipulate and to study the algebra of the generators, we see that in the algebra of generators appear some anomalous terms, which should not be there. But we can eliminate these terms if we fix the dimension, which up to now was an open parameter, was an arbitrary parameter. So we keep this dimension at a certain number so that this anomaly is cancelled. So higher dimension comes as, let us say, a consequence of eliminating dimension. It's not something that we put beforehand, but we put after we can close the algebra. We want to close the algebra of the generators. That's so it's a sort of quantum requirement. I mean, a requirement to give quantum consistency to the string. That is the idea.
Thank you very much, Jose. Thank you so much. More questions from the audience? Jeremy, yes, please.
Now I have a question. Do you think that the observation of emergent supersymmetry in this novel topological systems can give us some light of how can we broke supersymmetry in the nature?
Oh, I see.
Yes.
Okay, okay, I understand your question. Thank you so much for your question. It's a very important, interesting question. So I think, I mean, I go in a positive direction, I mean, by considering your question, because in these materials, for example, no, if we know that there is an emergent supersymmetry, and there are already, you know, there is already a good number of papers showing how we have this emergent supersymmetry, how it appears in terms of fields, in terms of excitations present in these materials. So by having this emergent supersymmetry, you know, and by knowing that these materials, they are not relativistic, you know, I mean, they have a dispersion relation which is linear, but the material is not relativistic. Instead of C, we have the Fermi velocity. So I think perhaps by making deformations in these materials, for example, no, they are topological materials. So maybe by making some sort of deformations in these materials, we can see how the emergent supersymmetry reacts, how it is broken. So if we deform the material or if we introduce some impurity in the material, how to see the response to this emergent supersymmetry. And so maybe we could have some hint on the breaking of supersymmetry by considering these materials. I think your remark is very important. And let us come back to the history of physics, and let us remember that the Higgs mechanism, which is so crucial for the standard model, and it was conceived in 1964 by a number of authors, no, Higgs, including Higgs, no, I mean, actually, the Higgs mechanism was for the first time, it was pointed out in the plasmon by Anderson. Philip Anderson wrote a paper on the plasmon excitations in materials. And he was, at the end of the paper, he was puzzled because some sort of excitation disappeared. So that was the Higgs mechanism. So let us say the Goldstone mode was disappearing because it was being absorbed by the photon to have a massive photon in the material, in the superconductor. So, I mean, the same way we learn, and Nambu, not only Anderson, but Nambu wrote a series of papers in 59, 60, 61. Nambu and Iona Lazinho, they wrote some papers. And I mean, based on this idea, how we have, let us say, a superconducting material. So we have, let us say, they tried to mimic that in field theory. So they wrote some papers on superconducting field theories. So that was a lesson to give mass, to the gauge bosons and to conceive the Higgs mechanism. We were fully and heavily inspired by condensed matter physics. So for me, it would not be a surprise if we try to get hints, to get trends on supersymmetry breaking by understanding the emergent supersymmetry in topological materials. I think that's a very important point.
Thank you.
More questions from the audience? If there are no more questions, we thank Jose for the very nice and very comprehensive talk.
No, thank you so much.
Thank you so much,
to
Jose.
you. Okay, so Antonio, thank you to you. Thank you to the colleagues in Santa Maria, and my friend Patricio is there also. My hug to Patricio and to people in Santa Maria. And okay, next time, okay, if later on we have to discuss more points, I'm always open, Antonio. Thank you so much for the hospitality. And every time I was going to Santa Maria before the pandemics, I had 4 or 5 visits to my friend Patricio in Santa Maria. I was, very kindly hosted by people. So I have very, very good memories of my stays in Santa Maria. So it was for me, I was very glad to meet you people again. And okay, Antonio, I met you in Patricio's office and you told told me that you are still sharing the office with Patricia. So if it happens that I go to Santa Maria sometime in the future, I hope to see you back in Santa Maria. Thank you so much to all of you.
It will be very nice that you can come soon to the Technical University Federico Santa Maria. We will have a workshop next year in January.
I know you have this traditional workshop. I have been once to do this workshop too. Thank you. So thank you, Antonio. I know that you are in Praha. No, you are in the Czech Republic. So enjoy your workshop there too. Bye-bye. All the best to you people. Bye-bye. Bye-bye.
Thank you so much, Jose. Bye-bye.
Ciao, ciao.
Bye.
Bye-bye. Ciao, bye. Bye.
Ciao.